Hi, I'm Colin. In this module, we're going to learn the algebraic technique of completing the square and then review several applications. Now, recall that the square of a binomial x plus y can be expanded as the square of the first term x plus twice the product of x and y plus the square of the second term y. As an example, consider the square of the binomial x plus 3. This can be expanded as the first term squared plus twice the product of x and 3 plus the second term squared. This simplifies to the quadratic trinomial x squared plus 6x plus 9. Notice that the middle coefficient, 6, is highlighted in red. That's because I want to make the observation that I can express the 3 inside the binomial along with the constant term 9 in the expansion in terms of this middle coefficient 6. Allow me to explain. Since the middle coefficient 6 is just double this 3, we can therefore say that this 3 is just half of the middle coefficient 6. And since this 9 is just the square of this 3, that ultimately means that this 9 is the half of this middle coefficient 6, then squared. So indeed, both these numbers can easily be expressed in terms of the middle coefficient 6 alone. In other words, if I blanked out the 3 inside the binomial, along with the constant term 9 in the expansion, then I could work them out from just the middle coefficient. This is in essence what the algebraic technique of completing the square is about. Specifically, if I started with the expanded quadratic x squared plus 6x, then what constant do I need to add to this so that we can factorize this combination into the square of some binomial? Well, from earlier, we know that this must be half the middle coefficient, all squared, which gives 9. And this is just half the middle coefficient only, which gives 3. We can summarize these facts into a nice formula. If I wanted to factorize the more general quadratic, x squared plus bx plus some constant as x plus some constant all squared, then the constant here is always half the middle coefficient, all squared. And the constant in the binomial is just half the middle coefficient, no squaring needed. Note that this formula assumes that the coefficient of x squared is 1. Let us now review some applications of completing the square. Because the technique is employed on quadratics, it is therefore incredibly useful given how frequently quadratic equations or expressions tend to show up in the mathematical sciences. First and foremost, completing the square can be used to solve quadratic equations. In fact, you may recall from classes that the derivation of the quadratic formula itself is only made possible by completing the square. Now, suppose we wish to solve the following quadratic equation by completing the square. We first divide both sides by the coefficient of x squared, not just to make the quadratic equation simpler, but to also get x squared on its own, so that we can complete the square later. We then move the constant term to the right-hand side. We now complete the square on the left-hand side. In fact, this is precisely the same quadratic on which we completed the square in the previous slide. Also note that we have added the required constant 9 to the other side of the equation too, in order to keep the equation balanced. As we saw in the previous slide, the left-hand side can then factorized into the binomial x plus 3 all squared. Notice that completing the square ultimately transforms the equation, so that the unknown variable x now appears only once in the equation, rather than twice. We then take square roots of both sides, and then simply rearrange for x. Completing the square can also be used to study and graph quadratic functions. For example, consider the following quadratic function. We studied this function and sketched its graph in two separate modules, one on finding the domain and range of quadratics, and the other on a topic called shifting transformations. It's a good idea to watch these afterwards if you've yet to do so. But in a nutshell, if I asked you to find the range of this quadratic function, which as you recall is the set of all the y values for the function, then it would not be obvious at all just by looking at the formula. In fact, a general strategy for finding the range of a function involves first sketching its curve. And on that note, if I ask you to sketch this quadratic function, then you'll ultimately want to find the vertex of the parabola, that is, its turning point. And it turns out that completing the square kills two birds with one stone, and allows you to easily find the range of the quadratic along with its vertex. We first complete the square on x squared minus 2x. Now, the half of negative 2 is negative 1, which when squared gives positive 1. We thus need to add this constant positive 1 to the quadratic. And at the same time, we also need to subtract it away at the end, so that ultimately we're still talking about the same function. The quadratic x squared minus 2x plus 1 then factorizes to the binomial x minus 1 all squared. Writing the original quadratic in this form tells us that the vertex of the parabola is at the coordinates 1, 2. Moreover, since the term x minus 1 all squared is always greater than or equal to 0, the function will always take values greater than or equal to 2. This allows us to deduce that the range is all the real numbers greater than or equal to 2. Again, you should watch the two aforementioned modules for more details. Finally, let's look at a special application of completing the square. Consider the following relationship between x and y. Although not obvious at all, it turns out that if we were to sketch the curve determined by this equation, then we get a circle. To see why, we're going to use completing the square to rewrite this given equation to be in the standard form for the equation of a circle. First, we move the constant 11 to the right hand side, and we also group together the x and y terms on the left hand side. We then complete the square on the two quadratics in terms of x and y respectively. Don't forget that any extra constants produced via the technique needs to be added to both sides of the equation here in order to keep the equation balanced. Each of the two quadratics are then factorized into the squares of binomials. We have thus rewritten the original equation in the following special form. However, from classes, you may recognize this to be precisely the standard form for the equation of a circle. Specifically, we have a circle here that's centered at the coordinates 1, 2, and has radius 4. Alright, I hope you found that useful. See you next time.